Hi class, this screencast that we're going to take a look at today is on phase changes. Phase changes are things that we're already familiar with. We already know that if we take ice out of the freezer and put it at room temperature, it will eventually melt. We know that if we leave a liquid such as water at room temperature and we leave it uncovered, eventually it's going to evaporate and it's going to become a gas. These phase changes are what we're going to study, and specifically we're going to look at the heat change that is involved with them. Now, you're hopefully already relatively familiar with the names of the phase changes: melt-in, freeze-in, vaporization, condensation. Those are going to be the main four that we're looking at with phase changes. We are not going to take a look at the heat involved going from a solid to a gas or a gas to a solid. But you need to know these names. But there is one that's actually kind of confusing. When we're talking about the heat that is required to melt something, the heat that is required to go from a solid to a gas, we call it, very strangely, the heat of fusion. So if you're ever calculating something, or if you're ever coming across a symbol that looks like this, the enthalpy, the heat flow at constant pressure, with a subscript FUS, that's talking about the enthalpy required to melt something. It's a really strange name, but that's what it is. So each of these components, fusion, freezing, vaporization, condensation, have a heat change associated with them, and because it's mostly going to take place at constant pressure, is an enthalpy associated with it. It is going to be true that the delta H of fusion, the amount of heat required to melt something, is going to be the opposite in sign of the delta H of freezing. The same is going to be true for vaporization and condensation. The amount of energy it takes to vaporize something is going to be the opposite of the enthalpy required to condense it. Same in magnitude, opposite in sign. These values are often expressed in kilojoules per mole rather than kilojoules per gram. So when you're calculating these, it's important that you are aware of the fact that I might give you grams and you would need to convert it first into moles in order to calculate the heat of fusion or heat of vaporization, for example. So if we take a moment to look at these two reactions that are written here, one is talking about ice becoming liquid water, and the other is about liquid water becoming water vapor. And notice what I've done is I've told you what the enthalpy change is associated with this if you have 1 mole of ice and if you have 1 mole of liquid water. The thing that I really want to focus on is the fact that these numbers are drastically different. It takes 6.01 kilojoules for us to go from ice to liquid water, and it takes 40.7 kilojoules for us to go from liquid water to water vapor. Why do you think that is? Well, the answer behind it has to do with intermolecular forces. If we think about it, when we're going from a solid to a liquid phase, we're overcoming some intermolecular forces, absolutely. But for the most part, there's still going to be intermolecular attractions between the liquid particles. When we're going from a liquid to a gas, it takes a lot more energy. We have to put in more heat because we're overcoming all intermolecular attractions. This is what leads us to see this stark difference between the enthalpy change of fusion and the enthalpy change of vaporization. And all substances will have this pattern due to the fact that going from a solid to a liquid does not break up as many intermolecular forces as going from a liquid to a gas does. We're overcoming all of them in that process. Phase changes are present in a lot of everyday experiences, but what we can actually do is we can calculate the heat involved in a lot of phase changes. So if I were to take a certain amount of solid ice at negative 20 degrees Celsius, and I wanted to know how much heat, how much energy I had to put in to raise it to 120 degrees Celsius, I would be going from the solid phase to the gas phase. And looking at this graph, there's actually 5 different heat processes that would have to undergo. It would go from being a solid at negative 20 to a solid at 0. That change in temperature has some sort of heat involved in it. It would, at 0 degrees Celsius, melt. It would then go from 0 to 100 degrees Celsius, in which case, again, that increase in temperature, we can relate that to heat. And then finally, it will boil, so that all the liquid molecules become a gas, and the gas molecules at 100 degrees Celsius are raised to 120 degrees Celsius. This is a great heating curve to have in your notes. If you have a different substance, you could have the melting point and the boiling point at different spots. But it's all going to follow the same curve. It's all going to follow the same idea. Something along these lines. Now, we're not yet at a point where we know how to calculate heat for a sample. But if we were going to, and if I asked you to take ice, a mole of it, at negative 20 degrees Celsius, and raise the temperature up to 120, it would undergo this sort of curve, and we'd be able to calculate the heat that's involved in part A, when it's still a solid, but it's just going from minus 20 degrees Celsius to 0 degrees Celsius. We'll take a look at this in class, but the equation that we're going to use involves the mass amount that we have, it involves the specific heat of whatever the substance is, in this case water, and it involves the temperature change. In part B, this solely involves that delta H of fusion and the mole amount that we have, in this case 1 mole. In part C, it looks exactly like part A. We'll calculate it very similarly. The specific heat changes from a solid to a liquid, but the temperature changes as well, but the mass will remain the same. In D, we'll once again calculate for the phase change, in this case for vaporization, and it'll be dependent upon the mole amount that we have. And then finally, we'll calculate the heat that's involved in going from 100 degrees Celsius of water vapor to 120 degrees Celsius of water vapor. Once again, that specific heat value will change. The delta T would be 20 degrees Celsius, but the mass would remain the same throughout all of this. Again, we'll go through a question like this in class, but before I end this screencast, I just want to say one more thing that might be surprising. Once a sample reaches the melting point or the boiling point, notice that the temperature is flatlined. The temperature does not change at the melting point or the boiling point until all of the sample has either melted or boiled, evaporated. The heat that is added at that time goes directly into breaking up those intermolecular forces. It does not raise the temperature at all. So there are a variety of different questions I could ask you from this. I could ask you to take something at 40 degrees Celsius and figure out how much heat is released when it goes to negative 20 degrees Celsius. I could ask you to go from 40 degrees Celsius to 120 degrees Celsius. There is a bunch of different questions that I can ask you from this, and we're going to take a look at the language in which the AP questions ask you so that we can make sure that we're calculating the correct thing. But that's it for this screencast. If you have any questions on any of this stuff, please don't hesitate to contact me. Thanks.